Welcome back, everybody. So this is Shiraz's second lecture. So let's get started. Over to you, Shiraz.
Thank you. Okay, so let's continue. So you remember that in the you might remember that in the previous lecture we sort of outlined a program to try to constrain classical gravitational scattering amplitudes using general low energy constraints. The goal was we were sort of motivated by this crazy sounding conjecture. The conjecture was that the set of all classically consistent classical gravitational scattering amplitudes was a very small set, and maybe consisting just of the Einstein scattering amplitude, the type 2 scattering amplitude, and the heterotic scattering amplitude. Okay, now in the previous lecture we talked about how we could try to make progress in trying to establish this conjecture. Okay, one way to try to make progress on this was to try to use low energy constraints to rule out scattering amplitudes that don't lie in this select set. As you remember, in these lectures we weren't going to be as ambitious as to try to establish conjecture 1 by itself. We were attempting to try to establish this slightly less ambitious conjecture 2. Okay, which was that the set of all scattering amplitudes for gravitational theory without higher spin fields, without arbitrarily higher spin fields, was just Einstein gravity. Okay, and we reviewed in the last lecture the argument by Kamano, Edelstein, Maldacena, and Zhibodev that essentially established this conjecture for the special case of 3 graviton scattering using the principle of causality, demanding that gravitational interactions cause a time delay rather than a time advance. Okay, and where we left off in the previous lecture was to try to find a second principle that may in the end turn out to be related to causality, but mathematically at the moment is distinct. To try to find a second principle that could allow us to constrain not 3 graviton scattering, but 4 graviton scattering amplitudes. And the principle that we hit on was this so-called CRG conjecture, the classical Reggie growth conjecture. And the CRG conjecture states that a classical theory of scattering grows faster than s squared at fixed t is physically unacceptable. Now, we quickly reviewed this signal model of CEMZ, of Appendix D in the CEMZ paper that suggested this was true. We discussed, however, that the signal model, while a beautiful argument and one that might well one day be turned into a theorem, at the moment had some deficiencies. And the deficiencies were serious enough that we weren't sure whether we could trust the final result from this argument or not. So we decided to search for another argument that maybe made a few more assumptions, but would whose results we could rely on for sure. Okay, and this was the argument that we had begun to discuss. That we're going to start this lecture by discussing the second argument, and the second argument is to try to establish this this conjecture. Or at least to give a strong argument for this conjecture, using the ADS-CFT correspondence and employing the chaos bound in the boundary field theory. So before I start outlining the argument in technical detail, I wanted to just give you in words a flavor for what we're going to do in this argument, so that you see where we're going. Okay, the spirit of this argument is this. One question you might ask is, how could we ever establish something about gravitational scattering amplitudes unless we have sufficiently well universal and sufficiently well understood formalism for gravitational quantum theories of gravity? Well, there are 2 ways in which one might proceed. Okay, one way would be to use some general low energy constraint, which even in the absence of knowing everything about quantum gravity, you might know that something must be true of a gravitational scattering amplitude if it is to be to describe a physically consistent theory. This is the spirit of the argument undertaken by CEMZ. They invoked the principle of causality, which we believe must be true of any good theory, whether or not we understand how it's quantum mechanically completed. Okay? But a second complementary approach might be the following. A second complementary approach might be to notice that we have at least one good and complete definition of quantum gravity using string theory, namely, in situations where you have an ADS-CFT type correspondence, the bulk quantum gravity is defined by the boundary field theory. Now, boundary field theory we really understand. So if we want to establish some statement about a bulk scattering amplitude, one route might be to try to establish it by appealing to known properties of the boundary field theory within the context of ADS-CFT. Okay, so this is the route we're going to try to follow. Okay, and just in a minute, what are we going to try to do? We're going to try to do the following. We're going to study a 4-point function. We're going to take some example of ADS-CFT. It could be n equals 4 Yang-Mills theory, or some other example of ADS-CFT, just some consistent example of ADS-CFT. Okay, and we're going to study a 4-point function. For gravitational scattering amplitudes, the 4-point function we will study would be of 4 stress tensors inserted on the boundary. Now, by studying this, now we're then going to invoke certain, we're going to use the fact that we know quantum field theory rather well. And so we know some things for sure about these 4-point functions of boundary correlators. One of the things that we know for sure is that these 4-point functions of stress tensors obey the famous chaos bound that Juan already alluded to in his lectures, and I will tell you a little bit more about as we go. Okay. Another thing that we also know is that in the situation in which the bulk dual of our conformal field theory on the boundary, the bulk dual of our conformal field theory on a boundary is a weakly coupled 2-derivative theory of gravity. Okay, of the kind that we want to constrain in our work. Okay, in that situation, there are certain kinematical configurations on the boundary in which the boundary correlation function develops a singularity. And this singularity has its origin in the fact that 4 particles can, from these regions, can go and scatter at some point in the bulk. This singularity is called the bulk point singularity, and has been studied in detail by various people. I'll have references as we go along. And one of the things that has been established in these studies is that the correlation function develops a singularity, and the coefficient of this singularity is the S matrix, the flat space S matrix of 4 very energetic particles scattering with the bulk interaction that generates the 4-point function on the boundary. So there are 2 things we already know in great generality about these kind of ADS-CFT setups. A, that if the theory in the bulk is the kind of weakly coupled gravity theory we want to study, somewhere in configuration space we have a bulk point singularity, the coefficient of which captures information about flat space scattering. B, we know that these correlation functions always obey the chaos bound. So our proof is going to be the following. We're going to use these 2 facts and use an analytic continuation to show that the bound on chaos obeyed by these correlation functions implies a bound on scattering, implies a bound on growth of the coefficient of this bulk point singularity. And we will find that this bound on growth implied by the chaos bound on the bound on growth on the coefficient of the bulk point singularity, namely the flat space S matrix, will turn out to be the CRG growth conjecture. Okay, so this is a rough outline of where we're going to go, and now I'm going to give this to you in some more technical detail. Okay, any questions or comments about the general philosophy before we proceed?
So Shiraz, can I just ask you if the following is correct?
Yes.
So your proof is going to assume the validity of the ADS-CFT correspondence. Is this the
yes,
correct thing?
This is correct. So what we're going so the statement is that in a situation where your gravitational first we assume validity of ADS-CFT correspondence. B, we're going to constrain our gravitational theories, assuming that they appear in the bulk of some ADS-CFT correspondence.
Okay.
So this is a weakness of the proof. It could be that there is some gravitational theory that exists in flat space, but it never appears in the bulk of an ADS-CFT correspondence. Okay. So great. But within the context of ADS-CFT, we're going to this proof will work.
Okay. Thank you.
Great. Thank you for that question. Any other question?
Yes, Shiraz, I have a question.
Hi,
it's the following sort of thing that is worrying me, that all these scattering discussions of causality, of even formulating the S matrix are in some asymptotic regions, or in regions where there is no gravity. Yes. I can well imagine myself, conducting an experiment and other experimentalists in a gravitational field, and also in which there are small fluctuations like gravitons. How do you formulate causality in such causality, S matrix, or how do you formulate this type of ideas where there is no artificial thing like asymptotically flat space-time, or some ADS box or something like that? In the bulk, how do you do this? Because we live in the gravitational field.
Right. So suppose we, perhaps what I didn't catch is, say the space that we live in is at least very well approximated by a flat space.
Yes.
Why do you object to going to, very far away in flat space, Spectre?
No, it's a possible, no, certainly one can formulate the problem and have good answers in such a situation. But it would be nice to also think in terms of sitting in the bulk. Yeah.
Yes, I understand. I understand what you're saying. No, that's an excellent question. The issue is this. For instance, within string theory, what we know how to calculate in, let's say, flat space are S matrices. Right? We don't know how to compute correlation functions at finitely separated points.
Yes.
Part of the reason for this is something I reviewed in the last lecture, that if you try to introduce local sources in gravity, it breaks diffeomorphism, it breaks general covariance. It breaks, the stress tensor is no longer conserved. So now this is not a full answer, because it would be possible to formulate some sources, for instance, sources of correlation functions of particles that are separated by a given proper length, but integrated overall. So just covariance allows for more general amplitudes than S matrices. But the easiest observables in the gravitational theory to formulate are those that are defined at infinity. That's why you try to define causality from things that are defined at infinity.
Yes, I agree with you. My point is that you're very worried about breaking general coordinate invariance and looking at only local operators which have the symmetry which aren't there.
Yes.
But an experimentalist naturally breaks general coordinate.
I know what you're saying.
Even in asymptotically flat space-time, where there is Poincare asymmetry, my watch is different from yours.
Yes.
And we know how to communicate then.
Yes.
I'm sorry to interrupt this.
No, not at all.
Procedures of yours, but I thought
it's an excellent
raise this question.
It's an excellent question. Certainly, within classical theories of gravity, one can address this causality issue the way Hawking and Penrose did. So this I sort of described last time a little bit, which is you set up an initial data slice that generates a space-time. Then you change the data slice only in a certain region and ask whether the change in the space-time lies within the light cone of the changed data region.
Yes.
Within classical gravity, that's something one can do and has been done for general relativity. And it has been proved that general relativity is causal by this criteria.
Yes.
Okay. Now one could try maybe to generalize this kind of analysis to more general theories of gravity. For instance, one could ask if something like string theory is causal by this criterion. I think it would be a very challenging job because you'd have to think through issues very carefully. But I think in principle, maybe you'd be able to do it. Maybe that's one answer. That does not refer to infinity because it takes a Cauchy slice and changes things on a Cauchy slice.
Right.
And the GR people, as we mentioned, don't go to infinity. Right? This is what they did. Hawking and Peng. Is that the kind of thing you have in mind, Spencer?
Yes. So, I mean, we can think of then, incorporating these ideas in the Wheeler-DeWitt equation.
Yeah, exactly. Now we'd have to formulate string theory in an appropriate way, and that will be a very challenging job, but maybe it's possible. Yes.
Maybe you need string field theory then to do
exactly.
this.
Something like that.
Yes, can it be studied in derivative expansion?
Ashok, I think I don't know. For instance, you could ask, it's just Einstein-Gauss-Bonnet gravity in 5 dimensions. Has this theorem been generalized or been checked? And I've never seen anyone do it. I suspect the answer would have to be that it will not work. Just because we know that the theory is acausal because of time delay, because of the time delay argument. But I've never seen anyone look at this analysis in this language.
I see.
Yeah.
Okay. Thank you.
Okay.
Sachin. Yeah. Sachin has a question.
I have a very quick question. So, there is also a correspondence between, let's say, D plus one dimensional flat space amplitude with a D dimensional CFT amplitude, right? It does not require any ADS CFT or anything, right? So, the kind of argument that you're saying that, the pole, coefficient of the pole is a scattering matrix, that exactly is the kind of thing that also appears there. So,
you mean like this celestial holography? No, sorry, what? No, maybe I didn't get the context.
Not celestial holography. Suppose I take, let's say, D-dimensional CFT. I take the flat space limit of it. Flat space in the sense that you take some certain energy, some momentas to zero. Let's say zero component of the momentas to zero. The coefficient of, the pole, coefficient of that pole corresponds to generally the, S matrix of one higher dimension.
And you're using ADS CFT or not?
No, not using ADS CFT. It's just the CFT correlators you can take in momentum space, not in Poisson space.
Oh, you mean kinematically?
Yeah, kinematically.
Kinematically. Now I understand what you're saying. Yes, please go on. Yeah.
So the kind of argument that you are using is basically some argument on the CFT correlators kind of argument to apply the argument on the S matrices, right?
Yes.
So is it necessary that I need to use ADS CFT for your proof? Maybe it is, but some constraint on the CFT correlator by using this kind of correspondence, one should be able to do in general, right?
Right now, I'm not so familiar with this kinematical statement you're talking about, Sachin. But would it effectively generate the S matrix of the corresponding theory in the bulk? Suppose I give you a particular correlation function. Okay, it could. Let's take the case where there is a bulk ADS. I give you a particular correlation function. There's some bulk operator which would generate that correlation function on the boundary. Now, in that case, if you apply your argument, would it effectively give you the S matrix of that bulk scattering amplitude in the bulk? Of that bulk interaction in the bulk?
1 second. Let me unmute him again. Yes. Sachin, go ahead.
Yeah. I'm sorry, sir. So I did not understand your comment. You are saying can you just repeat once more? Sorry.
Yeah. You give me. You said there's a correspondence between CFT correlation functions.
Yes.
And S matrices in one higher dimension.
Yes, that's right. That's right.
Okay. So now suppose I give you a particular CFT correlation function. So I take a particular example. The example I have is a situation where ADS CFT.
Yeah.
Okay. Now in that situation, I use the bulk to compute a CFT correlation function.
Yes.
Okay. Now on that CFT correlation function, I apply your map.
Yes.
Okay. It will give me some D plus one dimensional bulk scattering amplitude.
No, it will give me not bulk scattering amplitude. It will be like taking the ADS to the flat space limit, and then you will get flat space scattering amplitude. For example,
but some scattering amplitude generated by some bulk interaction.
Yeah, it will be generated by some. For your example, it will be generated by some bulk interaction.
Some bulk interaction, and will that bulk interaction be the bulk interaction that you put into ADS to generate your CFT amplitude? For instance, you started with 5 to the 4 on the bulk. You got your CFT amplitude.
Right.
You go back 5. Then it'll be the same thing. Then I think it will be the same thing.
Okay. Okay.
Yeah.
Okay. Okay.
Okay, so this map will be basically that of ADS-CFT, and maybe you can say it in other ways.
Okay.
Okay, but what will be important for me here is to see this structure as not emerging as a standalone thing, but as part of an analytic structure that includes the correlation function in different regimes, including the one which accesses the chaos bound.
Okay.
Okay, that's how we'll be able to connect it with the chaos bound.
Okay. 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 Thank you.
Okay, great, fantastic. So let's move. Unless there are other questions.
Yeah, there is a question in the chat box. Do you want me to read it out now?
Sure.
Yeah. So Joydeep is asking, last time you mentioned that you...
I can't hear you.
Yeah, can you hear me now?
Yes, I can hear you.
Yeah, last time you mentioned that using the treatment of perturbations in signal models, the partial wave can't grow faster than S at large S, which you mentioned translates to CRG conjecture.
Yes.
When you mean a clear proof from signal models, what additional ingredients do you require in addition?
Well, for instance, the signal model started with an assumption. And that assumption was that this Green's function, this G of omega that I defined in the previous lecture, that this G of omega is less than equal to 1 for all omega. Okay, this is very, where are we? This is very similar to what we get from scattering. Okay, because scattering amplitudes in partial waves, for instance, are less than equal, have modulus less than equal to 1. But this only this statement only really applies for physical omega, and those physical omega that are greater than 0. Okay, the argument that I presented required this statement to apply for all real omega, including negative omega. More along the same lines, the fact that scattering only applies at positive omega limits our ability to make wave packets that localize things in time. When you have things at positive and negative omega, you can localize things very well. So when you only have wave packets made, only about of positive omega, you can't localize things as well. And so you might worry that this whole framework of causality doesn't apply so well. Okay. Lastly, if you feel all of these are circumventable things, and they may well be, but if you feel all of these are circumventable things, something that I could point to is the fact that if you apply this argument to partial waves, okay, it's known. I mean, people from the 60s have studied these partial waves as analytic functions of omega and find quite bad singularities on the negative real axis. Okay, so not only, it's not just a formal thing, at least when you apply it to partial waves, that this thing is restricted to positive omega. Bad things happen at negative omega. Now, all of these may have a way around, right? It could be that the fixed impact parameter scattering amplitude is better behaved than the partial waves themselves. And I think that's roughly what CM said, believe. And there are other this business about localizing because you only have positive omega has other possible ways around it, some of which are sort of alluded to in the CMZ appendix. Okay, but having said all this, it's never been put together in a way that's completely convincing. That's what, in my opinion, that's what I had in mind. Is this? Am I answering your question, Jaydeep?
Yes, he says thanks. Yeah, so you can go ahead.
Okay, excellent. Fine. So now we're going to move to this discussion in the context of ADS-CFT. Okay. So as I said, I'm going to be studying the correlation functions of 4 operators on the boundary of ADS, namely in the conformal field theory. Now, for the purposes of my discussion, it's sometimes convenient to use what is called this embedding space formalism. Okay? So within this embedding space formalism, we want to describe ADS d plus 1. We describe it as the equation x square equals minus 1, a unit radius ADS d plus 1. We describe it as the equation x square equals minus 1 embedded inside R d comma 2. And my conventions are always, when I say R a comma b, I always mean the A coordinates have space-like indices and B coordinates have time-like indices. Okay, so suppose we're looking at R d comma 2, points in ADS points in this R d comma 2 that obey x square equals -1, and boundary points in ADS are null rays in R d comma 2. That is, they're null vectors in R d comma 2. Modulo the identification that any two null vectors that are equal up to a positive rescaling represent the same boundary point. Okay? I'm not going to, if you've never seen this before, I urge you to look this up in many places, including, for instance, one of the appendices to reference 3 in the lectures, where we explain all of this in great detail. We review all of this in great detail. This has been known for forever. Okay? So now what I'm going to do is to study 4-point functions inserted at 4 boundary points. The boundary points I'm going to describe in embedding space language. Okay? And here in my embedding space, the first 2 coordinates are the time-like coordinates and the remaining coordinates are the space-like coordinates. Okay? So the first point is embedded at cos tau, sin tau, 1, 0, 0, 0. Okay? Just to check that it's all making sense, remember I told you that a boundary point was a null ray. So it's some point in R d comma 2 that is null. Let's check that this is actually null. The norm on this space is this minus this squared, plus this square, plus this square, plus this square. But minus cos square minus tau square is -1, and plus 1 square is +1. So it's a null coordinate. Okay, so this is therefore a good boundary point. So the point P1 is this boundary point, P3 is this boundary point. Once again, we have cos square plus tau square, minus cos square minus tau square, plus 1 is 0. So it's again null. And similarly, P2 and P4 are these boundary points. Okay. And we're going to study these boundary insertions, assuming that these parameters theta and pi lie in these ranges. That is, tau lies between 0 and pi, and theta lies between 0 and pi by 2. This is convenience. It's enough for what we want to do. Now, I know that if I just give you some coordinates like this and I tell you it's in some embedding space, you can't form a picture in your head. But the way I've chosen these coordinates is so that tau here is what we normally think of as global ADS time. And theta here is one angle, or it's the angle on a circle on the boundary. So see, the first thing you should see here with what I've done is the following. You'll notice that all my embedding space coordinates have the 0 vector. All my embedding space coordinates are effectively in the first 4 entries. The first 2 entries were time-like entries. The next 2 entries were space-like entries. So all my embedding space coordinates were effectively in an R2,2 out of an RD,2. Okay. Now, R2,2 is the embedding space you would use to make an ADS3. And ADS3 is the dual to 2-dimensional conformal field theory. So even though the other coordinates exist, as far as for many purposes, you can imagine this just in a 2-dimensional conformal field theory. We're not in a 2-dimensional conformal field, but only 2 of the dimensions are active. There's an effective circle and a time that's active in these coordinates. We will see other coordinates, other parts coming out in the bulk, but at the moment to understand the boundary thing. Okay. So now you can picture this space really as a cylinder. So the boundary is really a cylinder. There's this spatial region, which is theta. Okay. And then there is time that runs up the cylinder. Okay. And then there is the radial coordinate that goes inside the bulk to make up the effective bulk space. Well, I'm only giving you a picture of the slice of this space that encapsulates the first 4 coordinates. But this gives you a sense of what the kinematics is like. The other coordinates exist, they're not there. But you can picture it thinking just of the first 4 coordinates. Okay. Now with this picture, these are the insertions that we have in mind. Okay. The coordinates 2 and 4 are in the future. They are t equals pi. The 2 coordinates are back to back. P2 and P4 are back to back with respect to each other. And they're back to back at an angle theta compared to some fixed axis. The other coordinates 3 and 1 are also back to back with each other. but at time slice that is to the past of t equals pi. In fact, this time slice is at t equals tau. Remember, we will allow tau to run from 0 to pi. Okay, and these two guys are back to back along our distinguished axis, namely this is theta equals 0. So now you get a picture for these insertions. We've got 2 in the future, 2 in the past, and there's a relative rotation of theta between them. And there's a time difference between these two coordinates, which is pi minus tau. Okay. Now that you understand the kinematics of the insertions that I'm looking at, one thing is very clear. One thing that's very clear is that these 4 points have some causal relations with respect to each other that depends on the details of these coordinates, tau and theta. So let's try to understand this. First, let's take the limit that tau goes to pi, so that these P3 and P1 are inserted at the same point, the same time slice as P2 and P4. In this case, all 4 points are inserted at the same time. So clearly the 4 points are, the causal relationship between the 4 points is that of Euclidean space. All 4 points are space-like related with respect to each other. Now, if we take this tau and lower it a little bit away from pi, that won't change. At some critical value of tau, though, this will start changing. This will change. Well, what is that critical value of tau? Well, it's easy to, if you think about it, it's easy to see. The answer is that critical value of tau is equal to, is pi minus tau is equal to theta. Because you see, the time difference between this and this is pi minus tau, and the space difference is theta. So when time difference becomes larger than space difference, for instance, the point P1 then transits to being in the causal past of P4, and P3 transits to being in the causal past of P2. Okay? So we concluded that when this tau is, when pi minus tau is less than theta, all these points are Euclideanly related with respect to each other. But when pi minus tau is greater than theta, so there's enough time for the signal to propagate, P1 is in the causal past of P4, and P3 is in the causal past of P2. Okay? For values of pi minus tau near theta, these are the only time-like causal relations. However, as we take this tau and make it smaller and smaller and smaller, so we bring this P3 and P1 lower and lower and lower down, at some point the time difference between these two becomes so great that not only can a signal from P1 travel from here to P4, that's already happening, it can now also start traveling to P2. Similarly from P3 to P4. Well, when does that happen? Well, that happens when the time difference becomes equal to the space difference. The time difference is pi minus tau, and space difference is pi minus theta. So it happens when tau is smaller than theta. Okay? So this kinematics here has 3 different causal configurations. When tau is near enough to pi, so that pi minus tau is less than theta, all 4 points are Euclidean related. When tau lies in such a range such that pi minus tau is bigger than theta but smaller than pi minus theta. Okay, P1 is in the causal past of P4 and P3 is in the causal past of P2, but P3 and P4 and P1 and P2 are space-like related. However, when tau is less than even theta, all the points here are on the causal past of all the points. Okay, so I've summarized that in this table here. When tau is greater than pi minus theta, I said it when I was saying it as pi minus tau is less than, whatever. When tau is greater than pi minus theta, all 4 points are Euclidean related to each other. We call such configurations causally Euclidean configurations. When pi minus theta is greater than tau is greater than theta, we call this the Reggie configuration. Okay, this is the configuration when P1 is in the causal past of P4, P3 is in the causal past of P2, but P1 and P2 are space-like related, P3 and P4 are space-like related. And finally, when tau is less than theta, we call these configurations are what we call the causally scattering configurations, where everything in the past, the 2 lower points are both in the past of the 2 upper points. Okay, great. Now, we have inserted our points. I've given you the insertion of points here, where we're putting our points. Now, we want to compute time-ordered correlation functions at these points. In order to, when things are not space-like related to each other, there are many different correlators you can compute. You have to be sure you're computing the right correlation function. One easy way to make sure you're computing time-ordered correlation functions, because that's what's going to be of interest to us in this talk, is to use the correct I epsilon prescription. Okay? And the correct I epsilon prescription is basically that you make sure that the imaginary part of your time coordinates, okay, is proportional to the real parts of your time coordinates. Because imaginary part of time coordinates determines operator ordering, and real parts determine the time, and we want the operator ordering to be linked to the actual time. Okay? So everywhere you see a tau, you just replace it by tau minus I epsilon tau, so that the imaginary part is proportional to the real part, and with the minus sign. If you work through the logic, you want that minus sign. So epsilon here is a positive number. Okay? So these are the I epsilon corrected insertions that we should put into our into correlation functions if we want to generate time-ordered correlation functions. Okay. Now, once we've done that, it's easy to, we've got our 4 points. We can compute the conformal cross ratios corresponding to these points, and we find the following formula. We find, for a minute, forget about the I epsilons. We find a formula which is 1 minus a cosine of something and 1 minus a cosine of something. Okay? You see immediately from this that these conformal cross ratios Z and Z bar in our configurations, okay, you see immediately from this that the conformal cross ratios in our configurations lie somewhere between -1 and 1, because cosine is bounded by -1 and 0, because cosine is bounded by +1 and -1. Okay, so both Z and Z bar are real numbers that lie somewhere between 0 and 1. Okay, and then this is slightly corrected by these I epsilons. Finally, just for notation, for some purposes, we will find it useful to modify, some functions of the Z and Z bar that people have used before. So we define Z is equal to sigma e to the power rho, and Z bar is equal to sigma e to the power minus rho. Okay, and since we know Z and Z bar, it's easy to compute sigma and rho. Fine. Great. So now I described to you, this kinematical configuration, and I described to you what happens as we take the insertion points, the lower insertion points, start at the same time as the upper insertion points and bring them down. Okay? I told you that causal configurations change 2 times as you do that. Now, typically, when causal configurations change in a Lorentzian correlation function, something interesting happens in the branch structure of correlators on conformal cross ratio space. So you could ask, what's the deal? What's going on here in conformal cross ratio space when you take these points here and bring them down? What's happening in conformal cross ratio space? Okay, well, what happens is as follows. First, let's look at Z bar. Okay. This diagram has been drawn with greatly exaggerated y-axes. I told you that Z and Z bar are always somewhere between 0 and 1 if you ignore the I epsilons. So let's say that we start at a point here, the place where we started, if we started really at tau equals pi, we started at a point where Z was equal to Z bar, that was this point. Now, as we take the time and bring it down, it's easy to convince yourself that Z goes towards this point 1 and then comes back. But because of the I epsilons, we can follow what it does when it comes back, and you can check that what it does is go circle around this branch cut and then comes back. Okay, and then comes back and then goes all the way here. So this green curve is what Z bar is doing. Okay, goes up to 1, comes back after circling this branch point. Okay, when does it circle this branch point? Well, it circles the branch point when you make the transition between the Euclidean and Reggie configuration. Namely, at pi minus tau is equal to theta, or theta is equal to tau is equal to pi minus theta. Similarly, you can follow what Z is doing in this conformal cross ratio space. Once again, you see that if you just follow, you ignore the I epsilons, you see that Z, instead of going towards the right, it starts going towards the left. It goes up to 0 and then comes back. Okay? But if you keep track of the I epsilons in detail, you find that it goes and circles the branch point here and then comes back. Okay? So once this passage is tau starting at pi, tau starting at, in my conventions, tau starting at pi and going all the way down to 0. Okay, so we start here at pi when everything's at the same time, and then we end up here at 0 after having circled around it. Similarly, we start here for Z, we start here at pi, we go circle round, and we end up back here at this point. Okay, so this is the passage. This is what the reflection of this change in causality as we move in kinematical space for this time-ordered correlation function. We're exploring the CFT correlators at different points, at different branches on this branch sheet. Okay. Now, in this net configuration space that we're looking at, there are two special limits of configurations that will play a very important role. One of them is the limit where we take tau to 0 with sigma held fixed. Okay, tau to 0 with sigma held fixed is just to make the time difference between these two insertions exactly pi at some fixed value of theta. Okay, tau to 0 with theta held fixed. Okay, that's easy to understand, right? I mean, when the two points are separated by, you approach the separation being exactly pi, but there's some angle between these two insertions. Okay, fine. Now, if you look at the conformal cross ratio rho, remember rho was defined as Z is equal to sigma e to the power rho and Z bar sigma e to the power minus rho. If you look at the conformal cross ratio rho, you find that in this limit, rho goes to 0 because tau goes to 0. Okay. Another way of saying it is that Z becomes equal to Z bar. The ratio of Z and Z bar goes to 1. Okay. Now you might wonder, fine, separating these guys by pi is something you can do, but why is that special in any way? The reason this is special is that this lands you on the bulk point limit that I talked about before. Okay, so I'm going to give you a 1-minute review of this bulk point idea. Suppose I take 4 points, 4 insertion points PA, and they're inserted somewhere. Thinking of PA as vectors in embedding space, I have 4 distinct null vectors in embedding space. Okay, generically, 4 distinct null vectors span a 4-dimensional subspace of RD, 2. This subspace cannot be completely space-like because it includes null vectors. So this subspace is generically either an R3, 1, has 3 spatial and 1 time directions, or an R2, 2. Okay. Now, if you study this question, you see that there's a bunch of configurations which have R3, 1, bunch of configurations which have an R2, 2. If you go, there's a boundary between these two configurations, between the R3, 1 and R2, 2 configurations. And when you go to the boundary, at least one way of going to this boundary takes you to a configuration in which what happens, the way that it makes a transition between this and that, is that of these 4 vectors, you suddenly develop a linear relationship between these 4 vectors. Okay, so now the space that you span is not a 4-dimensional subspace anymore, 4-dimensional subspace of embedding space anymore, but a 3-dimensional subspace. In fact, it turns out to be an R2, 1. Okay. It's a 3-dimensional subspace because there's a linear relationship between these 4 embedding points. Okay. And when that happens, whenever these 4 embedding points are not linearly independent viewed as vectors in RD, 2, but they're linearly dependent, you can always show that whenever that happens, rho goes to 0. Okay. Now, in our context, this happens precisely as tau goes to 0. Remember, it's hinted by the fact that rho goes to 0, yeah? And when tau goes to 0, it's very easy to just use these embedding space formulas Plug in tau equals 0, just sum these guys up, and you find you get 0. For instance, the first coordinate here is 1 plus 1 minus 1 minus 1, 0. Second coordinate, 0 plus 0 plus 0 plus 0, and so on. Okay? So the thing that is special about tau goes to 0 is at this point, the 4 embedding space vectors that describe our insertion points are summing up to 0. Now, why is that special? You know, this was the point of this bulk point paper. In the bulk point paper, they showed that whenever this happens, and provided some causality constraints are obeyed, which are obeyed in my situation, which I won't tell you about in great detail unless you ask. Okay, and whenever this condition happens and plus some other causality conditions are met, what happens is that the correlation function develops a singularity. The singularity is a singularity in this conformal cross ratio rho. You get a singularity like 1 over rho to some power, and I'll tell you later on what that precise power is. Okay, and the coefficient of that singularity is the flat space S matrix. Okay, is the flat space S matrix with some particular kinematics. I will tell you again as we go on in detail what the kinematic, I'll make that more precise. Okay, so this limit here, this limit where tau goes to 0, where these guys are separated by pi, is the bulk point limit. One easy way of seeing that something interesting is happening at this point is this. If you take the center of this cylinder, this is the point at tau is equal to pi by 2 and right in the middle. Okay, it's not hard to convince yourself that exactly when tau is equal to pi, for light rays from here can go and meet the center, and then light rays from the center can go and meet these 2 points. So this is a place where light rays can come, hit, and go back up. So it's a place where scattering can easily happen. Okay, and that's intuitively the reason why the correlation function becomes singular, and why the singularity has to do with the scattering amplitude. Okay, so this is the reason that the tau goes to 0 limit, or the bulk point limit, is special in our context. Okay, the second limit that will be of interest. Okay, maybe I should pause for a minute just in case anyone has questions about the kinematic setup that I've talked about, and in particular about this tau goes to 0 bulk point limit. Any questions or confusions about that? Great. Shall I assume?
I don't see any questions.
Yeah, perfect.
Maybe we can pause for 10 seconds to let people.
Sure.
Yeah, if anybody has any questions, then you can raise your hand and I'll unmute you. Nope, I don't see any questions.
Wonderful. Wonderful. I hope that means I was very clear, not that everyone is browsing the internet. Okay, excellent. Fine. A second kinematical limit that will be of interest to us is another and in a way even more interesting limit. This is the limit in which tau goes to 0. This is the limit in which tau goes to 0, but also theta goes to 0, in such a way that tau by theta is equal to a and is held fixed. Okay, so let's see what this limit is in this picture. Tau goes to 0, as we've seen, is that the time difference between these 2 points is pi. Theta goes to 0 is the statement that these 2 points are now just on top of each other. Okay, so in this limit, P3 and P1 are sitting here at tau equals 0, and P4 and P2 are going to these points. Okay, something you can convince yourself about is that in exactly these 2 points and these 4 points at tau equals 0 and theta equals 0 are points that are separated by a light ray that goes from one here to here and here to here. So this is a very a very tuned limit, a limit where one of the points, namely here P4, is on the light cone of P3, and another point P2 is on the light cone of P1. And right, these guys are just right on top of each other, and separated by a very special, by exactly the time difference that allows the light ray to go from here to here and meet. Okay, and then we're not exactly at this point because we've got this, we're approaching this point. Okay, with the ratio, how fast we approach in tau and how fast we approach in theta being held fixed as a ratio, and that's this quantity A. Okay, so this thing is called the Reggie limit. Okay, and in this limit, you can also compute the conformal cross ratios. Okay, and all the cross ratios become small because you see tau and theta, z and z bar both become small because tau and theta are both going to 0, and this is proportional to theta. Okay, now notice A is held fixed here. So because sigma was, z and z bar were both proportional to sigma, z and z bar is both small, sigma is small here. Okay. However, in fact, sigma squared goes like theta squared, or sigma goes like theta squared. Sigma squared goes like theta to the 4, sigma squared goes like theta squared. However, the ratio of z and z bar are not small. And so this quantity e to the power 2 rho, which was the ratio of z by z bar, that has a fixed limit in this ratio. Notice that this fixed limit goes to rho equals 0 at a equals 1. Let's see. So rho is equal to a equals 0. A equals 0. This rho goes to 0 as a goes to 0. And that is the statement that time is going to 0 much faster than space. And that was the original bulk point limit that we talked about, where we took tau to pi without taking theta to anything special. Okay, great. So this is the second limit that's of interest to us. Now again, you might say, well, it looks like a cute limit, but why are we, for physics purposes, why are we interested in this limit? Okay. And the reason we are interested in this limit is the chaos bound. Okay, so I'm going to try to explain this to you. By from the following analysis. See, first let's try to understand in these two limits that we talked about, we can ask what causal configuration were we in. So first, for the bulk point limit, it's very clear. For the bulk point limit, it's very clear because in the bulk point limit, tau was pi. But according to this formula here, as long as, tau was 0. And according to this formula, as long as tau was smaller than theta, we're in the causally scattering region, right? And that's clear. When the time difference between these two is pi and theta is something non-zero, these 2 points are in the past of these 2 points. So the bulk point limit happened in the causally scattering regime. And so on this diagram happened when this green arrow has gone around this point 1 and this purple arrow has gone around the point 0. Both have happened. Okay. What about the Reggie? What about the Reggie limit? Well, in the Reggie limit, theta and tau are both small. So clearly, we're not in the Euclidean regime because there's a big time between the points. And clearly, P1 is in the causal past of P4. Okay, and P3 is in the causal past of P2. But is P1 in the causal past of P2? That depends on whether, when theta approaches 0, or is P3 in the causal past of P4? That depends on whether theta is larger or smaller than tau. So it depends on whether A, our quantity, which was the ratio of theta and tau, was less than 1 or smaller than 1. Okay, so you remember we defined A as tau by theta. So when A is less than 1, okay, we're in the causally scattering regime. Both these points are to the past of both these points. But where A is greater than 1, we're in the causally regime, where P1 is to the causal past of P4, but P1 is not to the causal past of P2. And similarly. Okay? So this Reggie regime explores the region where this guy, Z bar, has gone around 1, and Z has either gone around 0 or not. It's not gone around 0 if A is greater than 1, and it has gone around 0 if A is less than 1. So you see the Reggie regime that we talked about spans 2 causal configurations, whereas the bulk point limit is in 1 causal configuration. Is this okay? Fine. Now, let us study the part of the Reggie regime which lies in the causally Reggie configuration, not in the scattering configuration. So the part that is A greater than 1. Okay? This part, this correlation function on this sheet has recently, and by recently I mean over the last 10 years or so, been studied in great detail. Okay? Now it's been studied in great detail, not in the kinematical configuration that I showed you, but instead by looking at conformal field theory on R1, 1 and studying some other set of insertions of operators. Now you may wonder, what's the deal? If you're on a cylinder, you're on the boundary of ADS and you're studying some configurations, why are you suddenly moving to R1, 1? And this is, the magic of conformal invariance. Conformal correlation functions depend only on a cross ratio and which sheet on that cross ratio space you're at. So if you manage to generate physics that lies at a particular cross ratio and on the same sheet in cross ratio space, you get the same physics no matter whether you started on a cylinder or on the plane, whether you started in one configuration or another. All that matters is what your cross ratios are and where on sheet space you are. Okay? So if you can find a configuration of 4 points on R1, 1 that has the same cross ratios that I told you about, and also is evaluated on the same sheet, meaning is evaluated on starting in Euclidean space and then going round the branch cut at z bar equals 1, coming back to this point, then you're studying the same physics. You get the same answers. Okay? And there is a configuration that people who study conformal field theories have been actively studying over the last 10 years or so, which is sometimes called the Reggie configuration. And this configuration is this. Consider 4 points on R1, 1, put the points 3 and 4 at space points 1 and space points -1 and hold them fixed. Okay? However, take the points 2 and 1 at some spatial point, let's say that's smaller than 1, and then boost these 2 points. So the boost sends 2 past the causal light cone of 3. When you start your configuration, you're in a Euclidean configuration. But when you take this and you boost it past the causal light cone of 3, it goes along this hyperboloid. And as you cross this light cone, you move. That is the same as taking your z bar and circling anti-clockwise around 1. Okay, and you do the same. It's the same boost acting on this particle 1. Okay, so this boost here generates some configuration. And when you take this boost to be very, very large, you're getting a configuration that is somehow very special, where these guys are going off very near to this light cone, and these guys are going off very near to this light cone. Okay. Now, even though these guys are going off very near to the light cone, it's easy to see that no matter what you do, I mean, it's clear from this diagram that no matter what you do, 1 is always space-like related to 2, even though it's clearly time-like related to 4. Similarly for the other guys. Okay, so this is the same causal structure as our causally Reggie configuration. And in fact, by choosing the boost appropriately, we can get exactly the same cross ratios we were studying. Okay, so this Reggie configuration that appears on our cylinder has been studied in great detail over the last 10 years in a slightly different context. Now, the reason that this Reggie configuration is of interest to us is that there is a theorem that bounds the growth of correlation functions as a function of this boost parameter in this Reggie configuration. Okay, and the theorem here, is the chaos bound. Now, I'm going to give you 2 minutes on how the chaos bound bounds this growth. The chaos bound, as you know, the configuration that I'm studying here is just the time-ordered correlation functions of these 4 operators. Nothing funny. Simple, standard, the things that we love to study. Okay? It's time-ordered when we look at this configuration in Minkowski space. However, if we take this we analytically continue this configuration to Euclidean space, this R11 to Euclidean space, and then take that Euclidean, that same Euclidean space, and quantize that Euclidean space with time not being, constant space slices not being these guys, but instead constant space slices being slices of constant R. A constant angle. Okay, this is so-called radial quantization of this theory. Okay, then you can show that the same configuration here, in the sense of radial quantization, okay, in the sense of radial quantization, is now an out-of-time ordered correlation function. Okay, and roughly the reason that we can see this is that, you see, if you take time which goes along these circles here, in this angular, maybe I should call it angular quantization. Time goes along circles, whereas in the first way of doing it, time went up here. So you see, along these circles, time goes in the same direction in the two quantizations on the right, but it goes in different directions for the two quantizations on the left. So because time is running in different directions, the notion of whether you're time ordered or not, okay, is different in these two quantizations. And it's not hard to convince yourself that the correlation function, and maybe Schumann will tell you more details about this in his tutorial session if you're interested. It's not hard to convince yourself that the correlation function that is just an ordinary time ordered correlation function in R1, 1, in this angular quantization kind of, where angular circles are time, okay, where the angle is time, okay, in this angular quantization kind of view, turns into an out-of-time ordered correlation function. Okay. Moreover, you see, because angle was time, in Euclidean space, time was a compact direction. Now, whenever you're doing a Euclidean calculation and time is compact, you're looking at a finite temperature computation. So you see, this correlation function, which was at zero temperature time ordered, zero temperature and time ordered in ordinary quantization, turns into an OTOC, an out-of-time ordered correlation function, an out-of-time ordered correlation function in angular quantization, and an out-of-time ordered correlation function in a field theory at a given temperature. This is the Rindler temperature. Okay, and using this connection, the chaos-bound people in Appendix A of the chaos-bound paper showed that their bound on chaos, which applies to out-of-time ordered correlation functions in any term at finite temperature in any quantum system, also applies here. But because there's the second way of viewing the same correlation function, the chaos bound now ends up bounding the growth of ordinary time ordered correlation functions in Minkowski space as a function of this boost parameter. Okay, so instead, this boost parameter was the analytic continuation of the circular time. So the chaos bound in thermal physics bounds the growth of out-of-time ordered correlation functions as a function of time in thermal things. But here, but since that time, the Lorentzian version of angular time was boost. What this does is end up governing the bounding the growth of these correlation functions as a function of the boost parameter. Okay, and specializing to a large N field theory, so that the chaos bound applies. The chaos bound in this configuration tells us that the normalized correlation function, normalized by dividing by these 2-point functions, cannot grow faster than a certain value of the boost parameter. Now, as you take this boost to 0, you can convince yourself, I haven't given you the details here, but you can convince yourself that sigma is going to 0. So as you go take the boost to infinity, sigma is going to 0. And in fact, the chaos bound tells us that this correlation function cannot grow faster than 1 by sigma as sigma goes to 0 at any fixed rho. Okay. Now, remember that here in the Reggie limit, this is precisely what was happening here. Our sigma was going to 0 at fixed rho. So the growth of correlation functions in this Reggie limit as a function of theta okay, as a function of theta at fixed rho is bounded by the chaos bound. Okay, so that's the reason for the interest in the second regime. Okay, I'm pausing here for questions or comments in case.
Yeah, there's a question in the chat box. Akhil is asking, are there also scattering growth bounds corresponding to higher point scattering, and do they correspond to corresponding chaos bounds?
Okay, excellent question. The answer to this question is, as far as I'm aware, not known either from the CFT point of view or from the scattering point of view. So Akhil's question is, the place where this is best understood is in CFT. So I think we should ask the question there first. Chaos bounds the growth of 4-point functions. Now you can ask, is there some sort of bound on 6-point functions when you in OTOCs? Now there's one obvious bound, right? If you take groups of operators where the groups are like 4 groups and take them as OTOCs, by using the OP for these 4 operators, you'll get basically the chaos bound on the effective operator that you would say. But the interesting question is, are there new genuinely six operator bounds that are not OPs of this 4 operator bounds? And I don't know of any. I think it's an excellent question and a very interesting question, but I don't know of such a bound. This is actually a key question to try to generalize for generalizing what I'm doing beyond 4 particle scattering. It would be great if there was such a thing. Similarly, on the scattering side, there's been no clear conjecture for such a high point thing. This is an excellent question, one that deserves work. Other questions or comments?
Yes. So Joydeep is asking, in the diagram of R11, is there any special significance as to why point 3 starts inside the light cone?
As to why point 3
starts inside the light cone?
Yes, actually it's point 2 that starts inside the light cone. This point 3 is at 1, so this is not point 1. Anyway, so the point 2 starts inside the light cone. Okay, if point 2 were to start outside the light cone, then what would happen is that we would be crossing a light cone in a slightly different way. We would be crossing this right light cone here. It's just a matter of detail. The physics is the same. It's just I had to choose one or the other, and so the physics was the same. Once you boost very much, it doesn't matter at all.
Okay. Shivam is asking, does this chaos bound only apply in the region of causally Reggie sheet?
Excellent. Yes, the chaos bound only applies in the causally Reggie sheet. There is no theorem for the chaos bound. There is no chaos bound type theorem in the causally scattering sheet. And this is the reason that it's not obvious that we can use these ideas to constrain scattering, because scattering is in the bulk point singularity that is in the causally scattering sheet. In fact, if you look at our configuration space here and ask what part of it can be translated into R11, turns out not all of this configuration space has a map into R11. Some part of it does and some part of it doesn't. And the part that is in the scattering sheet does not have a map to R11. So this diagram here only constrains what's happening in our setup on the Reggie sheet. Okay. Nonetheless, we'll be able to use analytic continuation to actually find a constraint on the scattering sheet. But we need that continuation. But excellent question. Other questions?
Okay, there are no further questions in the chat box.
Perfect. Okay. So now we know, we've understood our configurations. We've understood the physics of the 2 special limits we're going to study. And now we just have to proceed. Okay. Fine. What's, of course, really important here is that, as we've emphasized before, and as the question also asked about just now, this Reggie limit extends across two sheets. And in fact, we can be in the Reggie limit and start on the causally Reggie sheet and then change parameters so that we go to the causally scattering sheet. And then by taking A to 0, go and hit the bulk point singularity. So this is going to be very important to us. Okay. So now how do we go further? Okay. Suppose I take some correlation function, which is computed by the rules of ADS-CFT. For instance, in this, I'm going to focus on correlation function generated by a contact operator. So schematically, such correlation function takes the following form. It's given by 4 bulk to boundary propagators sewn together at a bulk point and integrated over all of the bulk. The bulk to boundary propagators have been listed schematically here. And the sewing together is the interaction which has been schematically listed here. Okay, so this is the kind of structure that we want to study. Now, in the strict Reggie limit, what happens when you set theta and tau to both to 0, what happens is that you develop 2 linear relations between these 4 points. Remember the bulk point limit, you developed a linear relation which was P1 plus P2 plus P3 plus P4 is equal to 0. In the strict Reggie limit, independently P1 plus P2 is 0 because these 2 points are just back to back to each other. And P3 and P4 are 0. Okay? So this collection of points P here spans an R11 out of R d comma 2. This embedding R d comma 2. So you can break up this embedding R d comma 2 into an R11 and R d minus 1 comma 1. And these 2 points are somehow in this Reggie limit. These 2 regions are sort of special. Okay. So here these are the R1 comma 1. And here these are the R d minus 1 comma 1. Okay. And so it's useful to parameterize points on ADS by using the coordinates U and V for these regions and the point Y for this R d minus 1 comma 1 region. Okay. The fact that we're in ADS, the condition x square equals minus 1 amounts to this equation. Now, this thing here is a d minus 1 dimensional hyperboloid. The Y is parameterized a d minus 1 dimensional hyperboloid whose radius is 1 plus something small or 1 minus something small. Something small because you can easily convince yourself that in the limit where these points go to these insertion points head towards this Reggie limit, the dominant contribution from the bulk integral comes from very small values of U and V. Okay. And so the bulk integral is given by some integral over this hyperboloid generated by Y's. Okay. And by massaging that bulk integral, and this is a lot of work and I'm not going to tell you about it. By massaging this bulk integral, one can do the following. One can show that this bulk integral goes singular in the limit that we go exactly to the Reggie point. Okay. The singularity comes from the vicinity of U and V very, very small. Okay. It's because all 4 propagators become very small in that region. Okay. And by analyzing this integral in great detail, one can show that the integral takes the following form. When you evaluate it, it takes the following schematic form. Okay. This integral now is a function of this theta and this A. Theta is going to 0 in our Reggie limit. A is being held fixed. Okay. The form that the integral takes is that there's some overall singular power of theta and some other overall singular power of A. This is relevant only when A goes to 0. And then there's overall singular power of theta and A are multiplied by a double power series expansion in theta and A. Or if you want, it's multiplied by a power series expansion in theta, such that the coefficient of every term in the theta power series expansion is itself a power series expansion in A. Okay. So this expression here is completely analytics, a power series expanded in both theta and A. So some power of theta, some power of A, and then multiplied by a double power series expansion. Okay. We can show this just by analyzing the bulk integral. I'm not going to explain to you how that works. That's a lot of work. Okay. Great. Okay. So in particular, leading order. At leading order in this expansion, we just take the term that the smallest power of theta that appears here. Okay, and that sort of by definition is H0 because we pulled out the power of theta so that this is non-zero. So this at leading order, this is theta to the power 2a prime minus 1 times a to the power delta plus r minus 3 times some function of a. where this function of A is, you can say quite a lot about it, but anyway, the important thing for us here is that it's Taylor series expansion. It has a Taylor series expansion around A equals 0. Okay. Now, recall that this analysis here was true everywhere in the Reggie limit, irrespective of whether we're in the causally Reggie regime or the causally scattering regime. Okay. So if we're in the now this function of A here, okay, this function of A, which had a nice power series expansion at A equals 0, has a non-analyticity at A equals 1. Okay, and A equals 1 is the transition between the causally Reggie and the causally scattering regime. But the other thing we can show is that this function here, while it's non-analytic on the real axis at A equals 1, it's completely analytic in the upper half plane, the A upper half plane. And so if you know what this function is here at A is equal to A greater than 1, you can find it for A less than 1 by analytic continuation in the upper half plane. Okay? And in particular, it's impossible for this function to be of this form, you know, in particular, something that's impossible is for this function to have like a theta function. It's impossible for there to be a theta function type dependence, like theta of A minus 1. So it's impossible for the power here to be unrelated to the power here because it's analytic in the upper half plane. Okay, excellent. Now this analytic continuation in A can be said a little more invariantly going to cross ratio space. If you take the quantity e to the power 2 rho, which is z divided by z bar, that quantity is this function of A. So as you take A from greater than 1 to less than 1, it's an easy exercise to convince yourself that what we're doing in this z divided by z bar, nothing funny is happening to z bar in this whole thing. So as what we're doing in the z analytic space is taking z around the branch cut around 0 like this. So as we take A from 1 to greater than 1 to less than 1, we're going around the analytic, the branch cut at z equals 0. Okay, so let me summarize. What have we concluded about this Reggie limit? About the Reggie limit, we've concluded A, that the correlation function becomes singular as theta goes to 0. The singularity is a particular power of theta. B, that the coefficient of the singularity is analytic in the upper half A plane. And C, the coefficient of the singularity, and in fact of all subleading singularities as well, are power series expandable, are completely analytic around A equals 0. Okay, great. So that's one of the things we established in our paper about the Reggie limit. Closely following work by Pulchinski and Sully and Penedones and so on, extending it to spinning particles. Basically, that's what. Okay, fine. So this is what we establish about the Reggie limit. Now, let me tell you a little bit more about this bulk point limit. In the bulk point limit, the bulk point limit, you know, on the scattering sheet, I've already told you that rho equals 0 is a singular point. And the singularity of at rho equals 0 captures information about scattering. Okay? This has been established starting in 2009, a remarkable paper by Gary Giddings and Penedones, and then established in a slightly cleaner way by Maldacena, David Simons-Duffin, and Sasha Zhivadev. We followed the analysis of this paper because it's technically easier for our purposes. But it's sort of equivalent to what they did here. In our paper, this analysis was done for scalar particles. In our paper, we generalized that analysis to particles with spin, and in particular to gravitons. Okay. So the final conclusion we reach in our paper is that when you've got 4 stress tensors outside here and we approach the bulk point limit, the correlation function develops a singularity as rho goes to 0. The structure of the singularity is completely controlled by universal sort of bulk physics. Okay, there are some coefficients which I've displayed here just to show that we can compute everything really exactly. You know, there's no twiddle anywhere. Then there are some kinematic factors of cross ratios which are out here, including, notice, sigma, which is like theta square to some power, and rho, which is like A to some power. And then an integral over a hyperboloid in in the bulk. And the integral in the hyperboloid in the bulk includes some kinematical factors as well as a bulk S matrix. Okay? And the bulk S matrix is the S matrix of, well, we worked it out for scalars, photons, and gravitons. So just forget about the scalars and the photons for a moment. Just focus on the gravitons. The bulk S matrix is the S matrix of 4 gravitons scattering in the bulk with particular polarizations and particular scattering momentum. Okay. Now I don't have the time to explain all the details of these polarizations and the scattering moment. Scattering moment are quite easy. I don't have the time to explain all the details of the kinematics. But the point is that this is a scattering, an integral over hyperboloid and ADS of a flat space scattering, where the details of the scattering depend on where you are in the hyperboloid. This is an element that's actually different for gravitons than for scalars. For scalars, the details didn't depend on where you were on the hyperboloid. For gravitons, it does. There's some technical details. Fine. What you want to take away from this here is that the bulk point singularity is in a very precise sense related to the scattering matrix of gravitons. And by analyzing this, it's easy to show that if the gravitons were to scatter in flat space, and this is just a the flat space scattering matrix. You can ask why when working in ADS do we get the flat space scattering matrix? And the answer is that this singularity has its origin in modes of extremely high energy. So the leading singular term cannot distinguish between flat space and ADS space. Okay. And okay, so by going through this, you can demonstrate that the following: that if the 4 graviton scattering amplitude were to grow at fixed t, but as function of s like s to the power a, then this coefficient that comes out of this formula, by plugging that behavior into this S matrix, the coefficient that comes out of this formula has a singularity in sigma or theta square as 1 over sigma to the pi minus 1. So that the growth, the Reggie growth of the flat space scattering amplitude determines the sigma singularity, okay? The sigma singularity of the coefficient of the rho singularity of this bulk point, namely the coefficient of the bulk point singularity. Okay, and now with all this preparation, the theorem follows in 2 lines. Okay, so recall that we found that in the sigma goes to 0 limit, the Reggie limit, the sigma scaling of our correlation function was 1 over sigma to the power a prime minus 1. Recall also that we found that that if we did the bulk point analysis, we found some scaling which was 1 over sigma to the power a minus 1. And now you can ask, what is the difference between the two? Well, you see, the bulk point limit happened when we first took tau to 0 and then took sigma to 0. On the other hand, our Reggie analysis was first taking sigma to 0 and then taking a to whatever value you want, namely maybe a to 0. So there's an order of limits issue here. Okay, we're going to the same point where both in trying to access the Reggie behavior of the scattering amplitude, we in the end up taking rho to 0 because we want the bulk point limit, and we end up taking sigma to 0 because we want Reggie scaling. That's what I've just tried to tell you here. However, there's another way of getting to the same point, which is first taking sigma to 0, that's Reggie scaling, and then taking a to 0, which is going to the bulk point limit. And the issue here is that these 2 limits may or may not commute. However, we've carefully analyzed the analytic structure of the Reggie limit. And remember, it was very important that we established that this h of a function here was a power series in A. So the extent to which these 2 limits may not commute is very limited. Okay. So here, when we took the theta goes to 0 limit first, okay, we got this 1 over sigma to the power a prime minus 1. However, if we first take the a goes to 0 limit so that we get the bulk point limit, it could happen that in the limit a goes to 0, h0 was 0 and h1 was 0, but h2 was not 0. In this case, we would get a higher scaling power. We would get lower singularity in theta, because we would have theta to the power 2a prime minus 1 times theta square, because we would get these HNs. Okay? The other way around cannot happen. So you see that the singularity of the bulk point limit, namely taking a goes to 0 first, in theta, is always lower than the singularity of the plain old Reggie limit. Okay? But the singularity of the bulk point limit was controlled by the growth, the Reggie growth of flat space scattering. Whereas the singularity of the Reggie limit was controlled by the chaos bound. So the singularity of the bulk point limit is always less singular than some upper bound that we know of from the chaos bound, which tells us that Reggie scattering of gravitons will always be bounded from above. Okay, and if you work that out, in mathematics, the fact that this is less singular. So this is the chaos bound tells us that a prime is less than or equal to 2, and the fact that bulk point scattering is less singular tells us that a is less than or equal to a prime. You combine these two, you find that a is less than or equal to 2. A was the growth of flat space scattering as a function of S, and therefore this is the CRG conjecture. Okay, so the end result of all of this, the end result of all of this is that we have demonstrated that at least within this, within the assumptions of the setup, ADS, CFT, contact interactions, and so on, we've demonstrated that CRG conjecture follows from the chaos bound. The demonstration is reasonably rigorous. I won't say it's mathematically rigorous because, well, whatever. Nothing I've ever done has been mathematically rigorous, but it's physics rigorous. It's a clean argument as far as I can tell. Okay, any questions or comments? And if the organizers allow, maybe I could have 5 minutes extra. I realize now I'm out of time, but it's just the beginning of lecture 2, so maybe I could just go through the first item in lecture 2.
Sure. Yeah, go ahead. Yeah, well, Shivam has a question. 1 second. Yes. Shivam, go ahead.
I have a question about this, the chaos bound. Are there any examples where chaos bound is violated? For example, some non-unitary theories which admits negative conformal dimension. And if yes, what does it imply about CRG conjecture?
Well, yes, there are examples in which the chaos bound is violated. For instance, I think Justin David and students studied examples of violation of chaos bounds or chaos type bounds in non-unitary high spin theories. In general, the proof of the chaos bound makes crucial use of unitarity. It starts with a Cauchy-Schwarz inequality, which comes from unitarity. Okay, now, so I think that in non-unitary theories, this could well be violated. Well, but that doesn't really impact the CRG conjecture, because you see, it's true that if you take a non-unitary boundary theory and you take the bulk dual of that, then that could now violate the CRG conjecture. But the bulk dual of a non-unitary boundary theory will be a non-unitary bulk theory, so it would not be a good theory. Right? So CRG conjecture is that this is obeyed for scattering amplitudes in good theories, in theories that obey all the properties we want. And unitarity is certainly one of them.
Okay, thank you.
Yes. Other questions?
Yeah, so there is a question in the chat box. Joydeep is asking, this A less than A prime statement, does this further constrain the chaos bound?
Does it further constrain less than equal to A prime? No, I don't think it further constrains the chaos bound. The chaos bound is what it is. And, I suppose the kind of thing that you might have in mind is that you say, well, if we can find a place where A is equal to A prime, then we know that the chaos bound is saturated. Well, A is equal to A prime in Einstein gravity. We know that the chaos bound is saturated. But these people always knew. The whole story of the chaos bound started by these calculations of Stanford and Cheng, who first realized that this bound is saturated in Einstein gravity, and then, So the kind of progress you might hope to make here is to say that this bound is as good as it can get, but we always knew it was as good as it can get. So I don't think it really says anything. Other questions?
Yes, Akhil is asking, has CRG conjecture been analyzed in the presence of background fluxes? This is referring to the idea that the chemical potentials and ADS safety violate chaos bound.
Chemical potentials, I see. Interesting. Yeah, you see, chaos bound, they don't, firstly, I think that's miswording of the statement. Chaos bound tells you that in the thermal ensemble, with no chemical potentials, there is a certain bound. Now, if you change the state with which you're working, you see, chaos bound tells you about growth of correlation functions in a particular state, namely the thermal state. It doesn't make any sharp claim about what happens in another state, which is not the thermal state. Now, for our discussion, we only needed to use the pure thermal state. Indeed, it would be very artificial for us to use anything but the pure thermal state. Because you see, turning on a chemical potential would be like turning on a holonomy in the time circle. Turning on a holonomy in the time circle in our R11 situation, okay, because we want to go to Minkowski space and time-ordered correlators, is turning on a holonomy in this angular direction. Now, holonomy in the angular direction is likely to be singular at 0. So this would be some strange operation in this R11 CFT. So I don't think that the fact that if by turning on holonomy, your chemical potential holonomies, you can mess around with that bound, has a very immediate and simple implication for scattering. Though it's a good question, and I confess I've never really thought it through. Other questions? I hope I answered the last question is what? I hope I answered the question that was asked.
Yeah, Akhil says thank you. Yes. Okay, Shiraz, you can continue.
Proceed. I'm sorry for taking extra time. I'll just take five minutes more. Just to set up where we're going. I'm sorry I misestimated my time so badly. I wonder how much of lecture 3 I'll reach. But anyway, so let's move on. So, fine. See, now let's focus on the road forward. What we've done so far is now established, given a pretty good argument in my opinion, for a condition that classical scattering amplitudes must obey. They cannot grow faster than s squared at fixed t. You might say, so what? Okay. Now what we're going to try to do is imitate the basic structure of the logic of the CEMZ argument. You remember what CEMZ did was follow. There were basically two elements in what they did. There was the important element, which was the physical constraint, namely that of time delay. And then there was the technically important but conceptually sort of trivial part, which was parametrization of possible graviton amplitudes. Now, in their analysis, they were very fortunate because they were going to try to constrain only 3 graviton scattering. And all 3 graviton scatterings were a linear combination of 3 basic structures. Okay? So they could proceed in the constraining very easily because of A times first, B times second, C times third. Okay? And then check which of these structures, if any, were consistent with their physical constraint and thereby get a constraint on scattering amplitudes. Now, we have just outlined the analog of the time delay constraint. We're going to use this CRG conjecture as the analog of the time delay constraint. Now, in order to proceed, we need to know something about scattering amplitudes that comes from kinematics. Okay? The problem here is that scattering amplitudes with 4 or higher particles are not parameterized by finite pieces of data. They're parameterized by infinite pieces of data. Okay? For instance, scattering of 4 scalars, identical scalars, is any function of S, T, and U. Okay, that's then crossing invariant. So any function of S squared plus T squared plus U squared and STU. Okay, fine. But that's a function of 2 variables, so that's an infinite amount of data. And when you add polarizations, it only gets worse. Okay, so what we need to do if we want to make sharp progress is to have an efficient way of parametrizing the most general 4-particle S matrix, taking into account this infinite amount of data. The nice thing about this infinity is that it's that if you restrict your attention to classical scattering matrices, these are scattering matrices which are polynomials apart from possible poles. if you restrict yourself to classical scattering S matrices, the polynomial part can be graded by derivative. And at any given derivative order, the number of pieces of data are finite. So derivative order by derivative order, one can completely classify all scattering matrices. Well, once you've got this complete classification, then you can impose the physical constraint of the CRG conjecture. You can demand that the scattering amplitude should not be allowed to grow faster than S squared fixed T. And when you do that, then you can ask which of these possibly allowed scattering, possibly kinematically consistent scattering amplitudes could potentially be consistent. This is the program we're going to run. And the program we're going to run now has a long technical part, which is to give you a complete characterization of all kinematical characterization of all possible S matrices. Okay, so there's going to be a long and exhausting technical part. And then once we're through with that technical part, we can apply our physical constraint on the most general parameterized data and ask which of these obeys our physical constraint. The remarkable thing is that the cut from this physical thing is very sharp. We will find that this constraint is hugely constraining, leaving us with only a finite number of possibilities, and for gravitational scattering with some assumptions. And indeed, in D less than or equal to 6, we will find that the only possible S matrix that obeys our constraints is the Einstein S matrix. Okay, so I suppose I should stop here. I will see what I will have to assess how much I can discuss in the last lecture, but I'll try that.
Okay. Thanks very much for this very nice lecture. Are there any further questions? So please unmute yourself rather than typing in the chat box. I think that's better. So if you raise your hand, I can unmute you and you can ask your question.
Okay, Shiraz, I have a general question.
Great, Ashok.
So the chaos bound is also related to the physics of black holes in the bulk, right?
Yes.
So can one just forget about the boundary theory and somehow relate the CRG conjecture with the physics of black holes?
Yes. I'll give you a guess, Ashok. I don't know, but I'll give you a guess. Actually, it's a guess about something I've tried on various occasions, and that Shayantani keeps trying, actually. But let me give you my guess. I suspect the following. My suspicion comes roughly from the viewpoint of fluid gravity conjecture and from the background of the fluid gravity correspondence as well as this large D analysis of black hole physics. But let me tell you what I suspect. Maybe there's something more direct, but I'll tell you what I suspect. Higher derivative theories of gravity, as you know very, very well, are consistent with the first law by this Wald analysis. Okay? And there is however, there is an interesting question about whether these higher derivative theories of gravity are also consistent with the second law. Now, there are many partial results about this, including the most recent beautiful ones by Shayantani, Nile and collaborators, following up on work of Wald. But all within an amplitude expansion around equilibrium. There is no clear understanding of whether it is true or not that something as far as I know, something as simple as Einstein-Gauss-Bonnet in 5 dimensions actually always obeys a second law, or whether it can violate a second law. I'll give you a conjecture. My conjecture is that if you study this question hard enough, you will find that Einstein-Gauss-Bonnet in 5 dimensions and all these other theories that we will rule out from violations of CRG will also violate the second law. Okay, that there will be no second law of thermodynamics for such black holes. And the reason this might be connected with CRG goes as follows. In theories with negative viscosity, theories that violate, in quantum field theory, you can prove that viscosity is positive from unitarity. But the positivity of viscosity is also essential for the second law, that entropy grows and is not destroyed. So somehow there is a tight connection between the second law and unitarity. And there's also a tight connection between unitarity and the CRG conjecture. So I feel that this might this might work out. Now, one last thing to say. You might ask how practically one can show this. I have the feeling that one might actually practically be able to show this at least in the large D limit. Because you see, in the large D limit, black holes are replaced by a membrane with its own fluid dynamics moving on that membrane. And over the last 15 years or so, the understanding of fluid dynamics has been improved a great deal. And without putting in this element of this fluctuating membrane, the question of which fluid dynamic equations are consistent with the second law or not has been completely cleaned up, starting with the work of Shantani, and then Mukund and Loga and Hongliu and so on. So, I think one might be able to prove, at least in large D and then possibly more generally, that all of these higher derivative theories of gravity are actually inconsistent with the second law. Not just that that it's hard to produce an entropy current that increases in this context, but that it's impossible to do that. Because one can prove such theorems in fluid dynamics. Give you fluid dynamic equations, you can prove that there's no entropy current consistent with these fluid equations. So I'm sorry for the length of this answer, but I feel that this might be one possible connection. There may be some more straightforward connection. Yeah, there may be some more straightforward connection, but yeah.
Okay, thank you.
Shivam, go ahead.
Yeah, I have a question just related to this higher derivative theories. I mean, if you take higher derivative correction of Einstein gravity, in that case, what happens with this chaos bound and CRG conjecture?
Okay, excellent. So something that if we get through these lectures, we will show that if you take, let's say, Einstein Gauss-Bonnet in 5 dimensions, and you just do a simple calculation. You compute the 4-point function of 4 stress tensors in the bulk on the boundary. You compute the S matrix of 4 gravitons in the bulk. This theory violates the CRG conjecture. Okay. This also tells you that if you compute the 4-point function of 4 stress tensors on the boundary, it will violate the chaos bound. So if you just take Einstein Gauss-Bonnet, that is an argument that tells you that such a theory is unphysical. Is this what you are asking?
Yeah, something related to it. Yeah.
Yes.
But
and
okay.
it's basically this is the spirit of what we're going to try to do. We're going to analyze all theories that violate the CRG conjecture. We will find that basically if you take a finite polynomial plus finite number of poles for gravity's S matrices, every such, in D less than equal to 6, every such theory violates CRG conjecture. And so if you put it in ADS, will violate the chaos bound.
Okay.
And so it's unphysical. Yeah. At least if you can put it in ADS.
Okay, thanks. Okay. Yeah.
Okay, yes, there's one more question. Let's see, Akhil. Yes, Akhil, go ahead.
Hi, am I audible?
Yes.
Hi, so I had 2 questions. One is like people try to relate this chaos bound with some hydrodynamics kind of argument where you think of some hydrodynamic mode exchange and so on. But then if you think about the energy perspective, that's like some low energy limit of the theory. And we are trying to say that the bulk points, the singularities are like really the high energy limit of bulk processes, right? So I'm just trying to square these 2 statements. Was that audible?
Yeah.
And second question is like since we were talking about causality and so on, there are 2 levels of causality, right? One at the boundary level, there's a boundary causality, and then that we know that like relates to some null energy conditions or something in the bulk. And then now we are talking about bulk singularities, which lands us on this CRG and chaos bound and so on. I was just wondering, like, could you like take this kind of this causality kind of arguments one level higher? Like if you start thinking about some 2 levels of holography or something, do you land on something more general, or is that a nice way to think about what we are doing?
Let's take your questions one at a time. The first question, I suppose I'm not familiar with what you're saying. Let's go back to Stanford and Schenker. Stanford and Schenker established, the first evidence from the chaos bound came from scattering in the bulk, and the scattering was essentially very high energy scattering, basically because of the boost factor of these modes near the horizon. So the original intuitive arguments for the chaos bound came from high energy scattering, and it's also related to high energy scattering in this bulk point way. Now, this business about the chaos bound being related to some hydrodynamic mode, are you thinking of like SYK and the exchange of the Schwarzian? Is that what you have in mind? Sorry, maybe you're muted. If you're thinking of SYK and the exchange of the Schwarzian, so what is the relationship between that and it's an excellent question. I don't know. Maybe Loga, somebody who's thought more about this in this language knows the answer. Somebody who knows. It sounds like a very good question. Why? It's true, right, that in the SYK theory, it's the exchange of the Schwarzian that governs the chaos growth. I think that's true. And how is that consistent with high energy growth? Somebody who's thought about this, maybe Spenta, maybe somebody who's thought more about this. I don't know the answer. It's an excellent question. Somebody knows the answer. I suggest they raise their hand and contribute.
So maybe it's the physics of the horizon that's sort of blue shifted from the physics of the boundary. Is that a possibility?
Yes, I suppose that's a possibility. I suppose I have not thought it through in this language. And did Hong Liu also have some papers about this? Loga, are you around and are you aware? Do you have an opinion on this?
Yeah, well, there have been various ideas of trying to.
You cannot hear. Cannot hear.
Sorry. Hello.
You're very soft, Loga.
Oh, okay. Sorry. Just give me 1 moment. Hello. Am I audible now?
Yes.
Hello. Yeah. Okay. Yeah. So the point is that so there is this thing that people say about pole skipping, for example, okay, which is which is some statement about something in hydrodynamics, but even that is not a completely low energy argument as such. I think so that is about if that's what you're referring to by Hong and collaborators. Now regarding the Schwarzian, I think in some sense, at least if you think about it from some higher dimensional extremal black hole point of view, in some sense, the Schwarzian is already some near horizon mode, right? I mean, I think this is probably also what Spenta meant in the sense that it's low energy from there may be some blue shift thing involved. Like what is low energy and what is high energy. Things I think regarding the Schwarzian, but I have not it's not completely clear what is.
I think it's a very good question, Akhil. I mean, if I have anything to say, I will email you. Yeah, thank you for the question. Now the second, now we've had so much discussion with the first question. I've forgotten your second question. If you could repeat it.
Hi, am I audible?
Yes.
Yeah, I was just wondering, again, this causality, right? You could break the causality kind of consistency relations at the level of boundary. Then that landed us on some null energy conditions in the bulk, this earlier works. And then now we are talking about causality from the bulk perspective, and that lands us on these growth conjectures and growth statements of the amplitudes of correlations. I was just wondering, could I go further? If I had two levels of holography or something like.
I see. Well, maybe I can make one comment about this. The comment is referring to the work of Hartmann and collaborators. You see, CEMZ had this. There was this nice argument about constraining 3.3 graviton scattering from causality in the bulk, and then CEMZ. And then Hartmann and collaborators translated that argument into the boundary. Okay, they basically argued that that if you consider a 4-point function of stress tensors, and it was generated by a bulk theory that included 3-point exchange that was not of the Einstein sort, then this 4-point function of stress tensors would run into trouble with general boundary properties. Now, I know they claimed that it was in the first part of the paper they talked about a problem with causality. In the second paper, which cleaned it up, they in some sense had to use the chaos method. So the comment I want to make is that bulk causality in this context has already been related to some boundary properties. And it's partly boundary causality and maybe something a little more. Okay, I don't think in the end, if the idea is that bulk causality and boundary causality are different things, I don't think that's right. The boundary theory being good will be the bulk theory being good. And maybe there'll be one good property in the bulk would be a linear combination of other good properties on the boundary and vice versa. But it'll be just shuffling around the same things. I don't think you will, there'll be a second level, if that's what you mean. Follow-ups or other questions? And the work of Hartmann and collaborators, where it shows that.
Yeah. So, any other questions?
Yeah, I had a question regarding something that was discussed a few minutes ago, not the immediate one. So this is about, the entropy being a way to constrain these higher derivative collections.
Yes.
So somehow, such an argument should admit the possibility of string theory, right? That you have infinite number of high spin tower, and then somehow that should be okay.
Yes.
So it should be somewhat subtle, right?
It should be subtle, but
kind of.
Yeah. Right. The argument, it's a little like what we're doing here. What we do here is to exclude the possibility of string theory by demanding that a S matrix is a polynomial crossed with a finite number of exchange poles. Okay. The fact that we're not allowing an infinite number of exchange poles is needed, and is the thing that excludes string theory. With that put in, we're able to use CRG to show that only Einstein gravity is okay. So somehow some analog of that would be at work. That the Lagrangian is some polynomial plus maybe a finite number of exchange poles. In that context, one should be able to show that the second law is not good. Now you can ask me, how are you going to be able to show this? I don't know. But again, let me say a little more. One more thought about that. You see, I think in general, it would be easy to show in that some idea of you make an ansatz for an entropy current on the horizon, and then it would be easy to show that it might be possible to show that within your ansatz there is no entropy current for certain theories of gravity. But in general, one would always run into the danger that one is limited by imagination in this ansatz. For instance, why are we, if we're in a theory of gravity and we're willing to look at fluctuations whose energies are such that the Gauss-Bonnet term can compete with the Einstein term. Okay, suppose we're willing to look at such structures. Are we sure that the structure will really live in the event horizon? Or event horizon in what definition of the metric? What field redefinition of the metric? Perhaps it'll live not on a surface, but on a volume and so on. There will always be issues of imagination. Remember that we're not trying to compute this entropy current and perturbation theory around Einstein gravity, because we know that the violations happen when the two terms compete significantly. Okay, so somehow I feel that in general, unless you have some guiding principle, it'll be hard to do something very concrete. But I feel that in the large D limit, there is a very concrete question, because now you relate this question to the existence or otherwise of an entropy current in fluid dynamics. And as you know, Loga, better than almost anyone in the world, this is a question one can answer in some abstract way, right? Given the equations of fluid dynamics, whether there exists an entropy current. Maybe one more thing to say about this. Maybe in the end, life will be even simpler. Ashok asked, well, and probably it's a tangent to Ashok's question, but let me say one more thing. As you know very well, you and Shantani and company had this theorem, right, in hydrodynamics, that if there is a set of hydrodynamic equations that admits an equilibrium solution whenever it should, and if that equilibrium is always stable, okay, then if the equations are consistent with these two properties, then the equations have a positive divergence entropy current. So this suggests that if some similar statement is true about gravity, the problem of these theories, the problem with these theories of the way these theories are sick, may actually show themselves up in equilibrium. It may be that if you take, let's say in the ADS context, you take an arbitrary boundary metric that is time independent, and ask for a black hole solution in Einstein-Gauss-Bonnet theory for an arbitrary boundary metric. A, either the solution does not exist, or B, that it sometimes becomes unstable. Could be something as simpler like that, and then that one might be able to show just directly at finite D. That's a simple thing. That's potentially a simple thing to show, the non-existence of an equilibrium solution. Sorry for the vagueness of all these thoughts. Sorry, Loka is, yeah.
Can I say something, Shiraz?
Yeah, say.
If you think about gravity is perturbatively just as a gas of gravitons that's scattering.
Yes.
I mean, I think many of these partition functions and other even non-equilibrium quantities can be expressed in terms of S matrices. I think people in the past have done things like that actually. So if you have a theory with a S matrix which is not allowed, then I would imagine that such a theory will not satisfy the second law.
Yeah. I have the same feelings, Penta. Also, Einstein gravity, unique in the theories of physics, has dual roles, right? In one context, the equations describe graviton scattering very much like Yang-Mills theory does. In another context, the same equations describe thermodynamics.
Yes.
Right, on black hole horizons. Totally remarkable. Right? So for this reason, it's very plausible that the equations that do something bad for scattering do something bad for thermodynamics. But I would love to understand them in better detail. I mean, I would love it. Ashok, do you have any? Does any of this sound plausible to you, or does it sound like nonsense? Maybe Ashok is not around.
Yeah, he's not around.
Okay.
He's gone. It's getting late, I think. So. Yeah.
Hey, I have one question of the organizers. Is there any chance my third lecture can be upgraded to a 2-hour lecture to give me some reasonable chance of completing the material I want to? Is that out of line?
I think it's going to be a little difficult because there's another lecture immediately after yours, around 3 o'clock. So just 1 second. Let me just check it. So your final lecture is on Friday.
Friday 11 o'clock.
Yes. And then there's another lecture by. Actually, no. We can do it. Yes. Yeah. We can do it for. We can have a 2-hour lecture on Friday.
Thank you so much, Anand. That gives me a fighting chance to complete the material. Yeah.
Sure. No, that's okay. Yeah.
Okay. Thank you.
Very good.
Thank you.
Okay.
Bye.
Okay. See you all. See you all at 7:30 tonight. Bye-bye.
See you. Bye.